Hey guys, welcome to this new video. Today I want to finally release the MiBand 9 and 10 custom firmware as it is right now. A while ago I showed a video on why both the MiBand 9 and MiBand 10 is not getting hacked at the moment, because at that time the SDK was nowhere to find for this BES2700iMP. And there are somehow good news, because a while ago I found the BES2700iHC SDK. And while this is not the IMP, it turns out it's good enough for us to run a custom firmware on the chip. You can see that the BES-IMP, which is inside the MiBand, and the IHC is a bit different inside. So you can see that the IHC is more made for like audio stuff. So you have a bigger audio blob, but no media basically. And on the IMP, you have a smaller audio blob and a multimedia and graphics part, which is basically the display controller, the QSPI, so quad SPI driver, and so on. And you can also see that the IMP has more RAM than the IHC. And together with the stock firmware out of the MiBand, I was able to reverse it far enough to get to a stage where basically Doom is workable, but I'm not super happy. Definitely better than nothing. As you can see, the display is really not fast and also not the right colors. And the reason is that I was not able to get this quad SPI mode running. It was basically sending the header for the display, but never transmitting the actual image data for some reason that is unknown to me. And I'm now using a one-wire SPI mode, which is far slower, and somehow the display is only accepting 8-bit color depth that way, so you can see how bad it looks. But it's something you would call. To get it there, I also needed to find out the flashing method, and there was another leak which is called this TWS earbuds SDK, and inside we have this DLD product line flasher, which basically is a Python tool to flash the SoC via UART. And every one of these SoCs there's a boot ROM, which is also mentioned in the manual or the very spare data sheet. And this tool did include like a lot of binary files, which turn out to be second stage bootloaders. And each of the SoCs has a different internal name. So while the MiBand SoC is named BES2700iMP, it turns out the internal name is BEST1503. And if we take a look at the leaked data, not data sheet, at the leaked SDK, we can see that there inside is the BEST1306 variant, but it's missing the actual BEST like 1500C, and only in one folder, like the codec folder, is still some parts of it. And if you search for it, there are some parts you can find of this BEST 1500 series. This meant that the SDK is working for the core, the basic chip basically, but not for that specific chip. As you can also see, the IHC has only 50 pin case, and the IMP has 170 pins. And turns out the IMP has like 80 GPIOs and the IHC only 30 or 40 or something. So including the reverse engineering of the stock firmware, I was able to get so far to support as much as currently available. And I just want to basically share this with you the way it is now. Maybe somehow you will find out how to drive this quad SPI mode. I tried so much things, and you don't want to know how much tokens are burned now via Claude to maybe figure it out that way and reverse engineering the stock firmware. Just to show how the reverse engineering of the MiBand 10 display and main connections really look like. You basically have like the logic analyzer connected to the Spring PCB to then again connect to the 32-pin connector on the MiBand PCB. You have like this flat connector here, and try to get every pin out of it. Funny enough, the MiBand 8 has the exact same pin out, but we still need to figure it out to know which GPIOs are connected to it. And maybe we can even look a bit closer this way. Just a little bit. It works better with the eyes. And then you basically check out what the interface is doing, what GPIOs are doing what. Create a custom firmware and try to do the same there. But yeah, this is really like hours and hours just to reverse engineer the BES2700iMP, or internally called BEST1503. Some more progress. Now the colors are a bit shifted, and it's still sending via 1-bit SPI, which is not the fastest one, but let's see how it goes. And would you look at that? Not only do we have screen fully working in the right colors and also text output, we also have touch inputs actually already working. Right now this is still software SPI, but in quad mode, and also software I2S. While it's not so bad on the I2S part, I2C part, this is bad for the display because it's just way too slow to print out to the screen, and I don't want to run Doom on this frame rate. So let's see how we can get hardware SPI. So either somehow the BEST1503 SDK gets leaked at some point, then we can drive the display as fast as possible, like with 7 millisecond for the complete display at like 500 times 200 pixel. That's crazy. And other than that, the pin out is also now found out. Previously, the MiBand 8 was using like an SWD interface, and I always was searching for it on the MiBand 9 and 10, but never found it because actually there is none, or it's not enabled. But by probing for UART pins, I was able to find out that that there are 2 UARTs basically brought out. One is the TXT of a debug interface. Basically, while everything is running, there are debug outputs, if enabled, of course. And the other 2 pins are the bootloader UART. And after powering the chip on, it will wait for 200 milliseconds for a message of the bootloader tool to write the second stage bootloader. And if so, you can communicate with it completely. And this allowed me to create also the BES2700 flasher, which now uses the second stage bootloader file to not only write the flash inside of the MiBand, but also is allowing to read the flash out of the MiBand. And by using, let's call it exploit more or less, we can also dump out the ROM from the chip with this second stage bootloader. And this allows to basically also read how the BLE is handling and how the ROM itself is working and so on. So this is also helping a lot to know more about the chip. Other than that, I will include some more videos of the progress of where I went when, basically. But overall, for now, I need to finish this up and upload it to GitHub. You can find it down in the description. You can see that, yeah, it's somehow working, but without the quad SPI driving, it will never be perfect. And my best guess is that the 96 megahertz clock is somehow not being enabled, while the slower SPI clock is fully working, so the header gets sent out correctly for the data, but this header is sent out slower, and only later the faster data transmission with this quad SPI is enabled and is working via the frame buffer tool inside of the chip and is transferring it via DMA, so you have the processing power free while doing the DMAing. And yeah, just to get it out there. Maybe you will find more. And overall, it's really like not an easy project for an unknown goal, really. I mean, of course, Doom, but what else?